Hi, നമുക്ക് ഇന്ന് ക്വാഡ്രുപോൾ ഇലക്ട്രിക് ക്വാഡ്രുപോൾ മൊമെന്റ്സ് നമുക്ക് നോക്കാം. ഇത് ഇങ്ങനെ ക്ലാസ് എടുത്ത് തരാൻ സാധിക്കുള്ളൂ. അപ്പോൾ ഇതിന്റെ നോട്ട് ഞാൻ നിങ്ങൾക്ക് ഇതിന്റെ കൂടെ അറ്റാച്ച് ചെയ്യുന്നുണ്ട്. അപ്പോൾ നിങ്ങൾക്ക് അത് വെച്ചിട്ട് നിങ്ങൾക്ക് ഒരു നോട്ട് എഴുതി തയ്യാറാക്കാം. അത് നോക്കിയിട്ട് ഓക്കെ. അപ്പോൾ നമ്മൾ സിലബസിൽ പറഞ്ഞ ആ പോയിന്റ്സ് മാത്രമേ നമ്മൾ ഡിസ്കസ് ചെയ്യുന്നുള്ളൂ. അതിന് പുറത്തേക്ക് നമ്മൾ പോകുന്നില്ല. അപ്പോൾ ഈ പറയുന്നത് ഈ നോട്ടിൽ തന്നെ ഉണ്ട്. നോട്ടിൽ നോക്കി നിങ്ങൾക്ക് നോട്ടാക്കി എഴുതുകയും ചെയ്യാം. വേറൊരു രീതിയിൽ നമ്മൾ എക്സ്പ്ലെയിൻ ചെയ്യാൻ പോകുന്നില്ല. അപ്പോൾ സിലബസിന് പുറത്തേക്ക് പോവുകയും ചെയ്യും. അപ്പോൾ നമുക്ക് ഇലക്ട്രിക് ക്വാഡ്രുപോൾ മൊമെന്റ്സ് എന്താ നോക്കാം. The calculation of electric quadrupole moments in the shell model is done by evaluating the electric quadrupole operator 3z square minus r square in a state in which the total angular momentum of the odd particle has its maximum projection along the z-axis, that is mj equal to plus j. Let us assume for now that the odd particle is a proton. നമ്മൾ ഷെൽ മോഡൽ ഇങ്ങനെ അറേഞ്ച് ചെയ്ത് ലാസ്റ്റ് ഇതിൽ ഒരു പ്രോട്ടോൺ നമുക്ക് ബാലൻസ് ചെയ്ത് വരുന്നുണ്ടെങ്കിൽ ബാക്കിയായിട്ട് വരുന്നുണ്ടെങ്കിൽ നമ്മൾ അതിനെ അതാണ് ഓഡ് പാർട്ടിക്കിൾ ഈസ് എ പ്രോട്ടോൺ. If its angular momentum is aligned with either z axis, then it must be orbiting mostly in the xy plane. അപ്പോൾ ഇതാണ് x axis, sorry z axis എന്ന് കൺസിഡർ ചെയ്യാം. ഇത് x, ഇത് y, okay, ഇത് y axis, ഇത് x axis, z axis. Then the angular momentum is along the z axis. Then the particle rotates in the xy plane. Okay. A more refined quantum mechanical calculation gives the single particle quadrupole moment of an odd proton in a shell model state J is given by the expectation value of QSP is equal to minus 2j minus 1 by 2 into j plus 1 into expectation value of r square, where r square for a uniformly charged sphere which is 3 by 5 r square. R square r നമ്മൾ നേരത്തെ കണ്ടിട്ടുണ്ട്, that is r0 a power 1 by 3. അപ്പോൾ നമുക്ക് r square r0 square into a power 2 by 3 നമുക്ക് എഴുതാം. A more disturbing difficulty concerns nuclei with an odd neutron. An uncharged neutron outside a filled subshell should have no quadrupole moment at all. അപ്പോൾ നമ്മൾ ഈ ക്വാഡ്രുപോൾ മൊമെന്റ് നമ്മൾ ചാർജ് പാർട്ടിക്കിൾ ആകുമ്പോഴാണ് നമ്മൾ മാഗ്നറ്റിക് മൊമെന്റ് ഒക്കെ നമ്മൾ പറയുന്നത്. ന്യൂട്രോണിന്റെ കേസിൽ ന്യൂട്രോൺ ചാർജ് ലെസ് ആണ്. അപ്പോൾ അതിന് മാഗ്നറ്റിക് മൊമെന്റ് നമുക്ക് എങ്ങനെ ഉണ്ടാവുന്ന നമ്മളൊരു ഐഡിയ, നമ്മൾ ക്ലാസിക്കൽ ഐഡിയ വെച്ചിട്ടാണ് നമ്മൾ ഇതിന് മൊമെന്റ് എല്ലാം നമ്മൾ കൺസിഡർ ചെയ്യുന്നത്. ഇതോ നമ്മൾ കുറച്ച് കഴിഞ്ഞാൽ പറയും ന്യൂട്രോണും മാഗ്നറ്റിക് മൊമെന്റ് ഉണ്ട്, ക്വാഡ്രുപോൾ മൊമെന്റ് ഉണ്ട്. When a subshell contains more than a single particle, all of the particles in the subshell can contribute to the quadrupole moment. Since the capacity of any subshell is 2j plus 1, the number of nucleons in an unfilled subshell will range from 1 to 2j. The corresponding quadrupole moment is expectation value of q equal to expectation value of qsp into 1 minus 2 into n minus 1 by 2j minus 1, where n is the number of nucleons in the subshell that varies in between 1 to 2j, and qsp is the single particle quadrupole moment. When n equal to 1, q is qsp. നമ്മൾ നേരത്തെ കണ്ടിട്ടുണ്ട്. But when n equal to 2j, corresponding to a subshell that lacks only one nucleon from being filled, the q is equal to minus qsp, so-called whole state. As q of particle is equal to minus q of whole. In particular, the quadrupole moments of the whole states are positive and opposite in sign to the quadrupole moments of the particle states. The model fails to predict the extremely large quadrupole moments of several bonds observed for certain heavy nuclei The explanations for these failures gives us insight into other aspects of nuclear structure that cannot be explained within the shell model. Okay. Valence nucleons. The shell model, despite its simplicity, is successful in accounting for the spins and parities of nearly all odd air ground states, and is somewhat less successful in accounting for magnetic dipole and electric quadrupole moments. The particular application of the shell model that we have considered is known as the extreme independent particle model. The basic assumption of the extreme independent particle model is that all nucleons but one are paired, and the nuclear properties arise from the motion of the single unpaired nucleon. This is obviously an oversimplification, and as a next better approximation, we can treat all of the particles in the unfilled subshell. Thus, in a nucleus such as 4320 Ca23 with 3 neutrons beyond the closed shell at n equal to 20, the extreme version of the shell model considers only the 23rd neutron. But a more complete shell model calculation should consider all 3 valence neutrons. For 4522 Ti23, we should take into account all 5 particles, 2 protons, 3 neutrons, beyond the closed shells at Z equal to 20 and N equal to 20. In addition to spin parity assignments, magnetic dipole moments, electric quadrupole moments, and excited states, the shell model can also be used to calculate the probability of making a transition from one state to another as a result of a radioactive decay or a nuclear reaction. Many of the tests of the shell model involve such nuclear properties as the spin and electromagnetic moments of the valence particles, all of which are concentrated near the nuclear surface. Likewise, many experimental probes of the nucleus, including other particles that feel the nuclear force, tell us mostly about the surface properties. Then even Z, even N nuclei and collective structure. Now let us try to understand the structure of nuclei with an even number of protons and neutrons known as even nuclei. As an example, consider the case 130 SN. The shell model predicts that all even nuclei will have 0 plus, 0 spin, positive parity, or even parity ground states. Because all of the nucleons are paired, according to the shell model, the 50 protons of 130 SN fill the G9 by 2 shell, and the 80 neutrons lag 2 from filling the H11 by 2 shell to complete the magic numbers of n equal to 82. To form an excited state, we can break one of the pairs and excite a nucleon to a higher level. The coupling between the two odd nucleons then determines the spin and parity of the levels. Promoting one of the G9 by 2 protons or H11 by 2 neutrons to a higher level requires a great deal of energy because the gap between the major shells must be crossed. ബാൻഡ് ഗ്യാപ്പ് മാതിരി ഈ ഒരു എനർജി ഉണ്ടാവും, എനർജി ബാൻഡ് അത് ക്രോസ് ചെയ്യണമെന്നാണ് പറയുന്നത്. Therefore, expect that the major components of the work functions of the lower excited states will consist of neutron excitation within the last occupied major shell. For example, if we assume that the ground state configuration of 130 SN consists of filled S1 by 2 and D3 by 2 subshells, and 10 neutrons out of a possible 12 occupying the H11 by 2 subshell. Then we could form an excited state by breaking the S1 by 2 pair and promoting one of the S1 by 2 neutrons to the H11 by 2 subshell. Thus we would have 1 neutron in the S1 by 2 subshell and 11 neutrons in the H11 by 2 subshell. The properties of such a system would be determined mainly by the coupling of the S1 by 2 neutrons with the unpaired H11 by 2 neutron. Coupling angular momenta J1 and J2 in quantum mechanics gives values from the sum J1 plus J2 to the difference J1 minus J2 in integer steps. In this case, the possible resultants are 11 by 2 plus 1 by 2 gives 6 and 11 by 2 minus 1 by 2 gives 5. Another possibility would be to break one of the d3 by 2 pairs and again place an odd neutrons in the h11 by 2 subshell. This would give resulting angular momenta ranging from 11 by 2 plus 3 by 2 equal to 7 to 11 by 2 minus 3 by 2 equal to 4, because the S1 by 2 and D3 by 2 neutrons have even parity and the H11 by 2 neutrons has odd parity. All of these couplings will give states with odd parity. If we examine the 130 SN level scheme, we do indeed see several odd parity states with spins in the range of 4 to 7 with energies about 2 MeV. This energy is characteristics of what is needed to break a pair and excite a particle within a shell. And so we have a strong indication that we understand those states. Another possibility to form excited states would be to break one of the H11 by 2 pairs and keeping both members of the pair in the H11 by 2 subshell. Merely recouple them to a spin different from zero according to the angular momentum coupling rules. The possibilities would be anything from 11 by 2 plus 11 by 2 to 11 by 2 minus 11 by 2. The two H11 by 2 neutrons must be treated as identical particles and must therefore be described by a properly symmetrized wave function. This requirement restricts the resultant coupled spin to even values, and thus the possibilities are 0 plus 2 plus 4 plus 6 plus 8 plus 10 plus. This is spin and this is superscriptive parity. There are several candidates for these states in the 2 MeV region, and here again the shell model seems to give us a reasonable description of the level structure. Of course, നമ്മൾ നേരത്തെ പറഞ്ഞിട്ടുണ്ട് the shell model description is only an approximation. Better approach is to recognize that if we wish to use the shell model as a means to interpret the structure, then the physical states must be described as combination of shell model states. Thus, psi of 2 plus equal to Si nu h11 by 2 cross nu h11 by 2 plus b psi nu d3 by 2 cross nu d3 by 2 plus c psi nu d3 by 2 cross nu s1 by 2 plus and so on. And here nu stands for neutron, and this cross indicates that we are doing the proper angular momentum coupling to get the 2 plus resultant. The puzzle of the low-lying 2 plus states can now be rephrased as follows. Each of the constituent states has an energy of about 2 MeV. In all but a very few cases, this 2 plus state is the lowest excited state. It's a general property of even Z, even N nuclei, valued throughout the entire mass range, independent of which particular shell model states happen to be occupied. There are other general properties that are common to all nuclei, and it is reasonable to identify those properties not with the motion of a few valence nucleons, but instead with the entire nucleus. Such properties are known as collective properties, and their origin lies in the nuclear collective motion, in which many nucleons contribute cooperatively to the nuclear properties. The collective properties vary smoothly and gradually with mass number and are mostly independent of the number and kind of valence nucleons outside of filled substance. The nuclei with A less than 150 are generally treated in terms of a model based on vibrations about a spherical equilibrium shape, while nuclei with A between 150 and 190 show structures most characteristics of rotations of a non-spherical system. Vibrations and rotations are the two major types of collective nuclear motion. The collective nuclear model is often called the liquid drop model, for the vibrations and rotations of a nucleus resembles those of a suspended drop of liquid and can be treated with a similar mathematical analysis. Then nuclear vibrations. Imagining a liquid drop vibrating at a high frequency, we can get a good idea of the physics of nuclear vibrations. Although the average shape is spherical, the instantaneous shape is not. It is convenient to give the instantaneous coordinate r of t of a point on the nuclear surface at theta of phi, as shown in this figure. Okay. Vibrating nuclear with spherical equilibrium shape. The time dependent coordinate r of t locates at a point on the surface in the direction theta phi. Okay. Equilibrium സ്റ്റേറ്റിൽ നിന്ന് വൈബ്രേഷനിൽ ഉള്ള ഷേപ്പ് മാറുന്ന കണ്ടോ, ഇൻസ്റ്റന്റേനിയസ് ഷേപ്പ്. In terms of the spherical harmonics, y lambda nu theta phi, each spherical harmonic component will have an amplitude alpha lambda mu of t. R of t equal to r a v plus summation lambda greater than 1 summation mu equal to minus lambda 2 plus lambda alpha lambda mu t y lambda mu of theta phi. The alpha lambda mu are not completely arbitrary. Reflection symmetry requires that this term equal to alpha lambda minus mu. And if you assume the nuclear fluid to be incompressible, further restrictions apply. The constant lambda equal to 0 term is incorporated into the average radius RAV, which is just R0 A per 1 by 3. A typical lambda equal to 1 vibration is known as dipole vibration. This dipole vibration is shown in this figure. Okay. Dipole vibration for lambda equal to 1, for quadrupole vibration, for octupole vibration. Notice that this gives a net displacement of the center of mass and therefore cannot result from the action of internal nuclear forces. We therefore consider the next lowest mode, lambda equal to 2 quadrupole vibration. നമ്മൾ ആ ഫിഗറിൽ കണ്ടിട്ടുണ്ട്. In analogy with the quantum theory of electromagnetism, in which a unit of electromagnetic energy is called photon, a quantum of vibrational energy is called phonon. Whenever we produce mechanical vibrations, we can equivalently say that we are producing vibrational phonons. A single unit of lambda equal to 2 nuclear vibration is thus a quadrupole phonon. The next highest mode of vibration is lambda equal to 3 octupole mode, which carries 3 units of angular momentum and negative parity. Adding a single octupole phonon to the 0 plus ground state gives a 3 minus state. Such states are also commonly found in vibrational nuclei. usually at energies somewhat above the two phonon triplets. As we go higher in energy, the vibrational structure begins to give way to particle excitation corresponding to the breaking of a pair in the ground state. These excitations are very complicated to handle and are not a part of the collective structure of nuclear rotations. Rotational motion can be observed only in nuclei with non-spherical equilibrium shapes. These nuclei can have substantial distortions from spherical shape and are often called deformed nuclei. They are found in the mass range 150 to 190 and A greater than 220, rare earths and actinides. A common representation of the shape of the nuclei is that of an ellipsoid of revolution, the surface of which is described by R of theta phi equal to RAV into 1 plus beta y20 theta phi, which is independent of phi and therefore gives the nucleus cylindrical symmetry. The deformation parameter beta is related to the eccentricity of the ellipse as beta equal to 4 by 3 square root of pi by 5 delta r by RAB, where delta r is the difference between the semi-major and semi-minor axis of the ellipse. It is customary to take RAB equal to R0 a power 1 by 3. When beta greater than 0, the nucleus has the elongated form of a prolate ellipsoid. When beta less than 0, the nucleus has the flattened form of an oblate ellipsoid. The quadrupole moment is Q0 equal to 3 by square root pi pi RAV square Z beta 1 plus 0.16 beta, where Q0 is known as the intrinsic quadrupole moment and would only be observed in a frame of reference in which the nucleus were at rest. For Q0 greater than 0, we would observe Q less than 0. The relationship between Q and Q0 depends on the nuclear angular momentum for 2 plus states Q equal to minus 2 by 7 Q0. The kinetic energy of a rotating object is half I omega square, where I is the moment of inertia. In terms of the angular momenta, L equal to I omega, the energy is L square by 2I. Taking the quantum mechanical value of L square and letting I represents the angular momentum quantum number gives E equal to h cross square 2I into I of I plus 1. For the energies of a rotating object in quantum mechanics, increasing the quantum number I corresponding to adding rotational energy to the nucleus, and the nuclear excited states form a sequence known as a rotational band. The ground state of an even Z even N nucleus is always 0 plus state, and the mirror symmetry of the nucleus restricts the sequence of rotational states in this special case to even values of I. We therefore expect to see the following sequence of states: E of 0 plus equal to 0, E of 2 plus equal to 6 into h cross square by 2I, and 2 e power 8 plus 72 h cross square by 2I, and so on. The first excited state is E2 plus is equal to 91.4 keV, and thus we have h cross square by 2I equal to 15.2 keV. The energies of the next few states in the ground state rotational band are computed to be E4 plus is 305 keV, measured as 300 keV, and so on. The calculated energy levels are not quite exact. We can gain some insight into the structure of deformed nuclei by considering the moment of inertia in two extreme cases. A solid ellipsoid of revolution of mass m has a rigid moment of inertia is equal to 2 by pi mr av square into 1 plus 0.31 beta, which of course reduces to the familiar value for a sphere when beta equals 0. For a typical nucleus in the deformed region, A approximately equal to 170. This gives a rotational energy constant h cross square by 2I rigid equal to approximately equal to 6 kV, which is of the right order of magnitude but is too small compared with the observed values, which is 90 kV. We can take the other extreme and regard the nucleus as a fluid inside a rotating ellipsoid vessel, which would give a moment of inertia I fluid equal to 9 by 8 pi mr v square beta, from which we would estimate h cross square by 2 I fluid equal to 90 keV. The fluid moment inertia is thus too small, and we conclude that the moment of inertia lies in between I rigid and I fluid. The rotational behavior is thus intermediate between a rigid object in which the particles are tightly bonded together and a fluid in which the particles are only weakly bonded. Another indication of the lack of rigidity of the nucleus is the increase in the moment of inertia that occurs at high angular momenta or rotational frequency. This effect is called centrifugal stretching, is seen most often in heavy ion reactions. Of course, the nucleus has no vessel to define the shape of the rotating fluid. It is the potential supplied by the nucleons themselves which gives the nucleus its shape. The next issue to be faced is whether the concept of a shape has any meaning for a rotating nucleus. If the rotation is very fast compared with the speed of nucleons in their orbits, defined by the nuclear potentials, then the concept of a static nuclear shape is not very meaningful because the motion of nucleons will be dominated by the rotation. The average kinetic energy of a nucleon in a nucleus is of the order of 20 MeV, corresponding to a speed of approximately 0.2 c. This is a reasonable estimate for the speed of internal motion of the nucleons. The angular velocity of a rotating state is omega equal to square root 2e by I, where E is the energy of the state. For the first rotational state, omega equal to 1.1 into 10 power 20 radian per second, and the nucleons near the surface would rotate with the tangential speed of v equal to 0.002 c. The rotational motion is therefore far slower than the internal motion. The correct picture of a rotating deformed nucleus is therefore a stable equilibrium shape determined by nucleons in rapid internal motion in the nuclear potential, with the entire resulting distribution rotating sufficiently slowly that rotation has little effect on the nuclear structure or on the nucleon's orbits. The rotational model is sometimes described as adiabatic for this reason. It is also possible to form other kinds of excited states upon which new rotational bands can be built. Example of such states known as intrinsic states because they change the intrinsic structure of the nucleus are vibrational states and pair breaking particle excitations. If the intrinsic state has spin different from zero, the rotational band built on that state will have the sequence of spins I plus 1, I plus 2 and so on. The vibrational states in deformed nuclei are of two types: beta vibrations, in which the deformation parameter beta oscillates and the nucleus preserves its cylindrical symmetry, and gamma vibrations, in which the cylinder symmetry is violated. Both the vibrational states and the particle excitations occur at energies of about 1 MeV, while the rotational spacing is much smaller. Both the vibrational and rotational collective motions give the nucleus a magnetic moment. A single proton moving with angular momentum quantum number L would give a magnetic moment mu equal to L mu n. However, the entire angular momentum of a nuclear state does not arise from the protons alone. The neutrons also contribute, and if we assume that the protons and neutrons move with identical collective motion, we would predict that the protons contribute to the total nuclear angular momentum, a fraction of nearly z by a. The collective model thus predicts for the magnetic moment of a vibrational or rotational state of angular momentum I, mu of I equal to I z by a mu n. For light nuclei, this ratio is 0.5 and mu of 2 is plus 1 mu n, while of heavier nuclei, the z by a ratio is 0.4 and mu of 2 is approximately equal to 0.8 mu n. Then more realistic nuclear model, both shell model for ODA nuclei and the collective model for even nuclei are idealization that are only approximately valid for real nuclei, which are far more complex in their structure than our simple model suggests. Moreover, in real nuclei, we cannot turn off one type of structure and consider only the other. The structure of most nuclei cannot be quite so neatly divided between single particle and collective motion, and usually we must consider a combination of both. Such a unified nuclear model is mathematically too complicated. ഇതിൽ നോട്ട് ഞാൻ അറ്റാച്ച് ചെയ്യുന്നുണ്ട് കേട്ടോ, നിങ്ങൾ അത് വെച്ചിട്ട് നോട്ട് പ്രിപ്പയർ ചെയ്തോളൂ.